In this video, we are now going to continue the derivation of the radiation from a magnetic dipole, an oscillating magnetic dipole. And so what we did, so now this is part 2. And what we did is before in the previous lecture, what we had is we set up the magnetic dipole like so, and then from there we started working on the vector potential, and we now have kind of written out the distances r, and now we're working on the cosine part. So now what I want to do is simplify this cosine function that we have here, which has a lot of stuff in it. It's got 2 cosines and it's got 2 sines. So we're going to apply another approximation. So this is going to be approximation number 2. Which says that the radius of this loop of current is much, much less than c over omega, which is essentially saying that it's much, much less than the wavelength of the radiation that's being emitted. So when we do that, I can take a look at my different terms, and I see that I have a term here, which is omega b times c and omega b times c. And so what this approximation is telling me is that omega b over c is much, much less than 1. Okay, so what's the effect of that? Well, the effect of that is that, you can kind of think of this as almost now like a 0. So that means the cosine is approximately 1, and the sine of what we considered a very small angle is going to be approximately what's inside there. It's approximately the angle. So it's not 0, it's just approximately the angle. So it's a small angle approximation for sine and cosine, essentially. Okay, so when I do that, then what I get is the cosine of omega t minus script r over c, which is what we started with, is approximately the cosine of the time-dependent stuff minus, now r, the position vector, minus omega b over c sine theta cosine phi prime sine of the time-dependent stuff. Okay, so we've achieved kind of getting away from using script r and putting everything now in terms of just the regular r, or I keep calling the position vector. Okay, so now we have that. Let's put it all together inside the integral for the vector potential. So the vector potential then is mu 0 I 0 b over 4 pi in the y direction, the integral from 0 to 2 pi of something very complicated, cosine omega t minus r over c minus omega b over c sine theta cosine phi prime sine of omega t minus r over c. Okay, close the curly brackets, times 1 over r times 1 plus b over r sine theta cosine phi. and then a cosine phi d phi. Okay, so in the end, we're only have to integrate over phi now. Okay, so let's work on some of these terms. We essentially have 1, 2, 3, well, we have a bunch of terms because we have a lot of parentheses to multiply through. Okay, so we can factor out the 1 over r right here. We can factor that out of the integral. And so, anyway, let's just attack it term by term. So open the integral, and what I would get is this cosine omega t minus r over c plus b over r sine theta cosine phi cosine omega t minus r over c minus omega b over c Okay. Okay. So what have I done? I've essentially, multiplied out the different terms. For in the previous equation, I multiplied through that parentheses and then factor out the 1 over r. So essentially now I have 1, 2, 3, 4 terms that I have to now integrate. And don't forget, I'm multiplying each of those terms by a cosine phi prime. Okay. So some of these aren't going to be too bad. Or, well, what I'm going to have is, I'll change colors now to red. I'll have a cosine phi for this term, cosine phi squared for this term, and then I'll have a cosine cubed for that term. So I have to take the integral of a cosine, cosine squared, and cosine cubed. Okay. Now, but to avoid the cosine cubed term, let's take a look at this and see that that term has a b squared in it. And if you remember approximation 2, our approximation 2 said that omega b over c was much, much less than 1, which now omega b squared over c is also going to be much, much, much less than 1. So we can throw that term away and reduce it even further to mu 0 I 0 b over 4 pi r y integral 0 to 2 pi cosine omega t minus r over c plus b sine theta cosine phi, and then that has a 1 over r cosine omega t minus r, or r over c, minus omega c sine close the square brackets there, and Actually, what I'll do is I'll change those, and this one, change that to red, so you can kind of see where that bracket ends, right there. Okay, and then, close the curly brackets, and then I still have a cosine phi d phi. Okay. Okay, so now we've reduced it down to essentially two terms. One that's going to be in cosine and one that goes as cosine squared. So if I look at the first term, then that is the integral of cosine phi to phi, which is 0. Okay, so this term right here drops out. And then I'm just left with the second term, which goes as cosine squared of phi d phi, and that is pi. Okay, so that's good. So then we'll go back and put this together, and I have A is then 4, no, it's mu 0, I 0, B squared pi over 4 pi r sine of theta times 1 over r cosine omega times the time stuff minus omega over c sine omega times the time stuff, and then close the brackets one more time, all of that in the y direction. So I can simplify things a little bit. The m0 is pi b squared I. So I can put in the magnetic moment. And so then I get A RT is mu 0 m0 over 4 pi sine theta over r times 1 over r times the cosine minus omega over r times the sine close the curly brackets, and now all of that is in the phi direction. So let me make some space. Okay, so now I should note that the author switches from the y direction to the phi direction without much explanation. And I think it's pretty much that he solved it in terms of y, because the x components canceled, but then essentially you can generalize it back to phi if you had chosen now maybe the point in the yz plane or instead of the xz plane.